Hi everyone, today I'll be going through a very quick demonstration about how to use an NMR resolution software called MNova towards solving NMR spectrums. And to help us do this, we'll be analyzing a sample spectrum of 1-nitro 4-phenyl ethanol benzene, and its chemical structure is shown right over here. Okay, so let's go right into it. So first up, open up MNova and clicking File, we can open up our MNova file. Okay, and we can see over here that we'll open up this folder. Open up the folder that is generated by your NMR machine, and we can see a whole set of files that are actually produced by your NMR machine. Our NMR machine is the Bruker NMR machine, and in that you'll see a certain file called a FID file, and the FID file, basically when you open it, it generates your NMR spectrum that was analyzed. Okay, so first up we see that there's a lot of blank space over here which is featureless, and we're going to cut that out first, but just by simply going into right here. Okay, just by clicking the zoom in button, we can highlight the region that we're interested in. Okay, right, next let's go back to our structure, and we can take a look at this structure. It's actually composed of benzene rings. So benzene rings connected by an alkyne group. And so if we know a bit about benzene rings, we know that, well, they are very shielded, and the protons should be more towards the left of the spectrum. More specifically, its spectrum, it should rely somewhere around more than 7. And so let's for now ignore this portion, and we're going to zoom in right into here. Okay, now let's say we're interested in this set of peaks first. So what we can do now is basically we want to select this peaks for analysis. And how we're going to do this is we simply go to peaking, manual threshold, and we can threshold to the peaks that we are interested in. Okay. And right off the bat, we can see that, there are a few numbers that pop up right up here. Now, these numbers look pretty small for now, so let's click on it. Well, not click on it first, right click on this to make our peaks a bit bigger. So right click, okay, properties, and we can go to peaks. Okay, by clicking peaks, click font, and we can make the peaks bigger. So let's make it about 14. Apply, and we can see that the numbers, the shifts are a bit bigger. We can have a better look at it. Okay, so now that we have chosen these peaks, let's now find out how many protons each of these peaks represent. Basically, we want to find the integration ratio. And now that we have selected these peaks, we can simply now click the integration button, and MNova will automatically integrate the peaks for us to let us know how much each peak is worth. Now, interesting thing is that this strong peak over here, if you notice, is automatically cancelled out. Not cancelled out, but ignored. It didn't integrate it because MNova actually, it has a database, and it did a comparison and said that this is actually a CdCl3 peak. And, it's a very common contaminant or common solvent used in NMR analysis. Okay, but let's leave that aside for now, because we are unsure whether our peaks are accurate to begin with. So leave it aside, and let's take a look. Remember that we are expecting 9 protons, and we see over here, let's round the numbers. 1.1, we're going to round to 1, 1.12 round to 1, 1.14 round to 1, 1.64 round to 1.64. Well, it's not an integer, it's not even close to an integer. So let's sum these numbers first. 1, 2, 3, 3.5, 1, 2, 3, 4, 4.5. Yeah. So the sum of all this integration integration area rounds to 4.5, which is a fraction. Well, it's 4.5. It's exactly half of 9. And this is where I was mentioning the symmetry of the molecule comes into play. So 4.5 times 9, well, this proton, because of its symmetry, this proton represents is identical to this. This is identical to this to this, and one single proton by its own. Okay. So using that, we can more or less kind of decide that these peaks are basically the peaks that we are just really interested in. So it seems like we are on a good footing for now, but let's try to decide how did we, well, let's try to assign these peaks actually. More specifically, we're more interested in how to find this peak, this set of peaks over here, and probably the set of peaks over here. Okay, so let's take a closer look. First off, we should probably take a look at the one closest to 1.5 right over here. And we see that, oh, it's not a very nice looking peak. In fact, yeah, it's not a very nice looking peak. Oh, by the way, we can increase the intensity just by simply zooming, rather rolling your scrolling a wheel, and we can see that it is 1, 2, doublet. It's split. It looks like a doublet of doublets. A doublet of doublets. So let's go back. Is that a doublet of doublet? So this proton is split by this proton is split by this, they're identical. Is there any splitting? It's hard to say. Well, this is hard to say indeed, because notice that it's 1.64, which implies that this, and this proton is bunched up together. And because this is split up by this, we get a whole mess of issues when this is also split by this, and it's not a nice spectrum. It's not a nice peak to resolve. But so let's assume that this is right for now. So sorry. Okay, when we can go back to the full screen simply by clicking this button, full spectrum. Again, we go straight back to our full spectrum. Go to the isolate to the peaks that we want right here. Okay, and now let's try to see where your other peaks are. Okay, so remember all this integration ratio, because of the symmetry, we should multiply by 2. So this represents 2, 2, 2, 3. Okay, so now let's try to expedite things a bit more. I've actually done a simulation using ChemDraw Ultra to try to simulate what this spectrum should what a spectrum for this molecule should look like, and it generated a spectrum that looks a lot like this. So let's try to compare them, and we can compare them simply just put it side by side. Take a look at its chemical shifts. Okay, so 7.32, notice that they're all lumped together, 3 protons lumped together, and look over here, it's about 7.32. It's a good estimate, so we can say like this set of peaks are good. Okay, this 2 protons closer to the alkyne is probably shielded a bit more, so we can say that this one should be about lower, more left of the spectrum, and 2 protons, well, it could be this one, likely to be this peak right here. Okay, and as we move towards your nitrile group, your NO2 group, we can see that your peaks, your shift starts to go higher and higher, and more specifically, this 2 right here are 8.16, as high as 8.16, and again we see that this over here shows a good prediction. Okay, so we can say that this set of peaks are probably representative of our sample. However, if we take a look again back at our spectrum, we see that there is a whole bunch of peaks over here. And now if this is our sample, so what are these? So what we can do now first is to basically maybe take a look at this peak specifically. Again, just a general feel, looking at this peak, pretty wide, could be water. This peak is pretty messy, could be contaminants, not sure what this is. So if we're curious, again, peek the peaks, and then integrate. And again, we see that when we integrate it, MNova gives us that this is a contaminant, or probably HDO, and hence explains why this peak is so wide. These are probably contaminants, this is probably contaminants as well. Okay, so let's go back to the full spectrum, and to close it up, we want to make this a snippet. We want to see make this part zoomed out on the spectrum, just for presentation's sake. So what we can do is first to do an expansion. So expansion, basically what we can do is a highlight, and it will generate a spectrum, not a spectrum, generate like a little box that can be zoomed out. And we can see, again, we can manipulate this by scrolling your wheel to get a better picture about what this part actually represents. So this helps you in data presenting skills. Okay, so right, so in summary, what I've covered in this little tutorial over here is how to use MNova. Basically, it's more basic functions, as well as to how to match certain peaks using by comparing against a simulation that we have. Okay, and finally, I've shown you how to present your data in a way that allows you to specifically show the entire spectrum and show peaks of interest. Hope this has been useful to you, and thanks for watching.